Hello, everyone. In this video, I'll be discussing transformers, groundbreaking neural network architecture that changed the world. First introduced in the famous paper, Attention is All You Need. It was written by Google researchers and scientists in 2017. Here are their names. First, let's start off with RNNs, recurrent neural networks, and their limitations. Sequential processing. Recurrent neural networks, RNNs, handle inputs in sequence, passing information step by step from one word or time step to the next. Due to the sequential dependency, they cannot easily leverage parallel computation. They have vanishing and exploding gradient problems. Training RNNs, especially for long sequences, can be challenging due to the problems of vanishing or exploding gradients. This makes it difficult for the network to learn relation between distant words effectively. Long-range dependency problem. RNNs struggle to effectively capture dependencies between words that are far apart in the sequence. The information from earlier parts of the sequence can be diluted as it propagates through the network. For example, the cat sat on the hat. By the time the sentence gets to the word hat, it has already lost the original meaning of cat forehand. Another problem is computational bottlenecks. The sequential nature and the complexity of the RNN calculations contribute to significant computational costs during both training and inference. Alrighty, attention mechanism. Here are the advantages of it. Parallelism. Instead of processing words one at a time, the model looks at all the words in a sentence simultaneously. This significantly speeds up the processing. It focuses on relevance. The attention mechanism allows the model to determine the relevance of different parts of the input sequence to each other, effectively establishing a relation between words without relying on sequence processing. Parallel processing. This architecture allows parallel processing of input, significantly speeding up training and inference. In a global context, unlike RNNs, which must process information sequentially, the attention mechanism can directly attend to all parts of the input sequence simultaneously. And here I'm going to explain it's called in 5 steps, the attention mechanism, how it works. First, let's start off with embeddings. Each word in the input sequence is first converted into a dense vector representation called an embedding. This vector captures semantic information about the word and is typically learned during the training process. Example, the cat sat on the mat. The is vector 1, cat is vector 2, sat is vector 3, and etc. until mat is the last vector. Query key and value vectors. Each word's embedding is then projected in 3 separate vectors. Q for query is used to represent query when attending to other words. K for key is used to compare with the query vectors to determine relevance. V for value, used to construct the output representation. Example, for the word cat, you have the vectors of Q cat, K cat, and V of cat. Third step is the scale dot product. Well, scoring is a dot product. The query vector of a word is multiplied using a dot product with the key vectors of all the words in the sequence. This results in a score representing the similarity or relation between each word in the query vector. Example, the query vector for cat, query of cat, is compared with the key vectors of the cat, sat, on, the, and mat. The strongest match is likely with the key vector set. And over here, on the right, I have the attention equation they have. And I have the math more scale, math softmax, and math multiplication. The attention score. The similarity between each query key is calculated using the dot product attention QKV softmax of q k to the power of t square root of d over k of v. The scaling factor square root of d of k is crucial for stabilizing gradients, preventing dot product from becoming excessively large, especially with high dimensional key vectors. The softmax normalization, the scaled scores are passed through a softmax function to produce a probability distribution over the input words. These probabilities represent the attention weights, indicating the relative importance of each word in the sequence. The scores from step 3 dot product become weights. Cat might have a high weight for sat, 0.7, a moderate weight for mat, 0.2, and a low weight for the rest, 0.1. This is just examples. The weights can vary depending on the words and on the models. Fifth, the weighted sum, the contextual representation, attention weights are then used to compute weighted sum of the value vectors. This results in a context-aware representation of the word, considering the relevant information from the entire sequence. Example, the updated representation of cat combine its own vector of cat with vector of sat and vector of mat weighted by the attention score. This produces a context-aware embedding of cat. Multi-head attention, capturing multiple perspectives. The transformer utilizes multi-head attention, which means that the attention mechanism is applied multiple times in parallel, each time with different learned weights in the matrices Q, K, V. I have an image over here on the right showing the representation of that, and all the images are from the research paper. This allows the model to capture multiple relationships and aspects of the input sequence simultaneously. Think of it as looking at the same information through different lenses. Here is the transformer architecture, encoder and decoder. Here you can see where the input happens. Multi-head attention at normalization, feed forwards at normalization. Multi-head attention adds more normalization, feed forwards, the linear softmax, and the output probabilities. The transformer employs a stacked encoder-decoder architecture utilizing self-attention feed forward layers. The encoder on the left side is composed of 6 identical layers. Each layer contains multi-head self-attention, allowing the model to attend to all positions in the input. Position-wise fully connected feed-forward network MLP. Residual connections around each sublayer facilitating gradient flow. Layer normalization after each residual connection. Also, layer embeddings layers produce output of simultaneous. There's 512 layers. The decoder on the right is composed of 6 identical layers. Each layer contains multi-heads of attention, masked to prevent attending to future positions. Encoder-decoder attention attending to the output of the encoder stack, position-wise fully connected feed-forward network. Masking and self-attention prevents each position decoder from attending subsequent positions, crucial for autoregression regeneration. Here are some training regulation details that the model used. They used the English to German and the English to French dictionary with various what's called parameters. Here's 4 point, English to German had 4.5 million sentences. The English to French had 36 million sentences with 37,000 tokens and 32,000 tokens, respectively. The hardware they used was trained on one machine with 8 NVIDIA P1000 GPUs. The base model is zero point 0.4 seconds per step, trained for 100,000 steps, and the bigger model was trained for 1 second per step for 300,000 steps, around 3.5 days. Here is the atom optimizer parameters they used. The learning rate varied. They used an equation that varied. Regularization, residual dropout. Applied to the output of each sublayer, residualization, residual addition, and normalization. The p drop equals zero point 0.1 in the base model. Also applying the combined embeddings and positional encodings. Label smoothing used with epsilon of L of S, zero point 0.1, making the model less overall confident, which improves accuracy in blue scores. So the main advantages and impacts. Parallelization. Pretty much enables faster training inferences compared to recurrent models due to the inherent parallel nature of self-attention. Long-range dependency capture allows direct relationship between any two words, regardless of distance, mitigating the vanishing gradient problem and better capturing long-range dependencies. Interpretability. The attention mechanism provides valuable insight by visualizing attention weights, aiding understanding model behavior. Transfer learning. Adaptability to new tasks by pre-training on extensive data sets for generalized language represents patient and efficient fine-tuning for specific downstream MLP problems. This has huge impacts and implications. It revolutionized natural language processing. The transformed paradigm shift fundamentally reshaped the landscape of NLP and has created high resulting performance in NLP tasks. Foundation for SOTA model architecture foundation, new generation of powerful large language models. It improved performance in key tasks such as machine translation, key text summarization, question answering, and text generation. Everybody knows about ChatGPT and Grok. Broad capabilities used across many fields, including text, translation, sentiment analysis, speech recognition. It is scalable. The model scale well with increased data and model size, leading to better performance. In conclusion, attention is all you need. Introduce the transform model. This revolutionized processing. The architecture relies solely on the attention mechanism, abandoning recurrence. It showed that attention can replace previous architectural choices like RNNs. The main key takeaways are that the transformer is faster, more efficient, long-range dependency and model interpretability. The architecture has become the foundation of state-of-the-art results across a wide range of NLP tasks. The models enabled the development of modern large language models. Looking forward, the impact of this approach extends far beyond MLP, including fields like computer vision, audio processing, and many more. The transformer architecture has initiated ongoing research, includes further improvements, model efficiency, and exploration of new applications. Thank you for your time.